Okay, can everyone see that? Question 8?
Yep.
Okay, good. So that's week 9's question 8. So the question is, liquid chlorine added to swimming pools to combat algae has a relatively short shelf life before it loses effectiveness. Records indicate that the mean shelf life of a 5-gallon jug of chlorine is 2160 hours. So we know we've got a mean that we're trying to test. So, and the 90 days doesn't really matter because it's the data that we've got. As an experiment, hold longer, an additive was added to the chlorine to find whether it would increase the shelf life. A sample of 9 jugs of chlorine had these shelf lives in hours. All right, so they want to know at the 97.5% level, which is a pretty stringent level of confidence. Okay, that's a pretty tight level. It's above 95%. And 95% is usually the approach. So that's usually the benchmark that you use. Now, this one is not an in-between equal, not equal hypothesis test. This one is a greater than or equal to test. So if you take the approach that the null hypothesis is the additive had no effect whatsoever on the shelf life of the chlorine, and then let me prove otherwise with a 97.5% confidence that it actually did. So that says the null hypothesis is that so again, if we were to adopt this hold longer and use it in perpetuity as a savior to our chlorine, we're going to consider that the population of our chlorine inventory or our chlorine going forward. In other words, we'll adopt this going forward, and that'll be our entire population because we'll live with it for forever, essentially. So that's why we're going to use the population as the model that we want to test against. So if we take the hold longer didn't really do anything, so it didn't do anything, the null hypothesis is that it's going to be less than or equal to 2160, meaning it had no effect on our chlorine levels. We want to disprove that if we can, and we're going to use the alternate being it actually did. So if we take a look at the curve is going to actually have, so let me see if I go up to, I believe I put this, I didn't do this one. Okay. I usually put the rule curve at the top of the assignment. Let me go see if I can find one and just pull up that picture because I think it's a decent picture to actually look at. I think week 10 may have actually had, they actually had that. All right, so I'm going to switch over real quick. Actually, no, I'm just going to take this picture. I'm going to copy it, and I'm going to paste it to the document that we're looking at. So can everybody still see the week 9 question 8?
Yep.
All right. So basically, Control V. Nope, wrong one. Go back, try it again. Copy. So I want to copy this and paste this in here. All right. So here is the actual model or the test we're going after here. So it's a right-tailed test, meaning we want, if we're going to reject this null hypothesis, we have to be out here. So our critical value that we calculate has to be greater than this critical value for this data set. Now that's an example there. It's not going to necessarily be 1.645. But what we're trying to do is say, all right, if we get a value that exceeds the critical value out here, then there's something to that. It actually does, based on our data. Now, what is it? 1, 2, 3, 4, 5, 6, 7, 8. It's 9, which isn't really a huge data set. You'd probably want, you know, at least 20 or 25 in your data set in order to really be happy with it. But that's okay. I mean, that's the data set we're given. So this is the test that we're looking for. We're kind of say, all right, prove to me that it really does, because I'm not adopting this, or I'm not going to add this because it'll be additional cost to my product unless you can prove that it actually does. So our null is that it doesn't, and then we want to prove otherwise that it does. So our critical value is 2.306. So that happens to be the critical value. So if we were to actually look up the degrees of freedom and go into the t-table and use 0.025 as the one tail, we could either look it up in the t-table, or I prefer using the R script called, let me pull that up. I believe I actually have this somewhere. All right, yeah. So let me switch over to my R script and share my screen. R Studio. This is in the week 9 folder. It's called using the t-test. Actually, no, what is it called? It's called, so it's in week 9's R script, and it's the second to last from the bottom. And it is called R script for calculating t-test using the t.test function. So essentially, instead of having to manually sort of run through all of the mechanisms or the mechanics of that that hypothesis test, that t-test, we're actually just going to use the simple R script. And I think I said in an email, I hope I did anyway, that would be going forward from week 9, probably the preferred R script to use for calculating t-tests. Why? Because it's very simple, and we're going to use the R test for this. So I did a couple things here. This is an example in that R script, which is essentially concatenating all of the data values into a data frame. So that's one approach for doing the data. Again, I've wanted us to learn how to manipulate CSV files, because you're going to encounter lots of CSV data out there in your travels when you become informatics professionals or data scientists or analysts or whatever you're going to do in this field. So it's really good that you get used to using CSV files, because that ends up being the common denominator for most data sets. So if a data set sits in some proprietary database somewhere and you need the data, well, it can always be generated. A CSV can always be generated from it. So you can always get a CSV file. That and JSON files these days are kind of the new data set, JSON files, called JavaScript Object Notation. They look a little different. Well, actually a lot different. They're essentially, they're what are called, well, they fit the NoSQL object model. We're not going to get into that, but that's just a different way of reading the data set in. And actually R has a JSON parser as well. So, but we're going to use CSVs for now. So I've either got this data set, or I could uncomment it, and I have a chlorine test.csv file that I created, and the heading on it is called shelf life. So I just put shelf life in A1. So I could pull that file up real quick. Downloads. Chlorine test. And I'll switch my screen over to that. And there is my screen. So here's my shelf life, and I just basically keyed that in and did a file save as, making sure that I choose the CSV comma delimited option. All right, so hopefully everybody's been working through that, and they've got, they've had their ability to understand how to do that. So that's that file. There's your data set. Let's go back to R. And now so I'm going to comment. Let's just do that. Let's just use the concatenated data frame for now, just something different. Like I said, at all the R scripts, we count the number of rows we read, just in case the code doesn't work. You could always go back and say, hey, did I read the data file? Did I get the expected number of data entries that I was expecting? Now, I calculated mu here because the problem told us that mu was 2160, I could have easily just done a mu calculation here on that data set and just dropped a variable in here, but I'll leave it as the 2160. Now, we have to tell the R t-test function which test we're using. So we need to tell it an alternative. So in this case, the alternative hypothesis is greater than, meaning the t-test function is going to know, hey, we're looking for an upper tail rejection region, and we're looking for this picture that we saw. So let's go back to that again. It's this. No, it's not that. It's this.
Professor, I'm sorry, that script, is that in the week 9 folder?
It is. It's the second to last folder, or it's this. I'm sorry, the second to last script in that folder. It says t-test with a t.test function.
Okay, thank you.
You're welcome. So it literally is that script right there that you just saw. So I'm going to close this out real quick. So that makes that calculation very easy for us. All right. So since we're telling the t-test function, there'll be 3 different kinds of parameters you can send to that t-test function. One is upper tail or lower tail. So if that script was less than, then the alternative would have been the other way. It would have been this test right here. We'd be going the other way with it. All right. So you can tell the t-test R script function which side you want it to test for. So we're testing for critical value, the rejection region being up here in the upper right. So if I go back to the R script now, stop, and I'm going to come back to the R script, and I run this. So let's just do a quick check on my data set. 9 values. Let's look at the R output. The R output is right here. So it calculated a t value, a t statistic for me of 3.9791, and it also calculated the p-value. So right there, that tells us, even looking at that p-value being less than 0.05, more likely than not, we're going to reject the null hypothesis. All right. And the t-test actually does that. It says, oh, you should choose the alternative hypothesis in this case. So if we go back to the solution, so essentially what this is saying is, oh, wow, we did see a difference in the shelf life of chlorine based on this additive. So there may be something here that we should look at. All right, so let's go back to our Word doc again and share that. And then here is the here's the solution to that. So there's our hypothesis test. The chlorine didn't, or the additive didn't do anything and prove otherwise. Well, guess what? It did. Our rejection, or our critical value, is 2.306. Our t statistic based on our data set is 3.97. That puts us out here. So we're going to reject the null and accept accept the alternative. All right. So reject H0, the mean chlorine shelf life has increased. The p-value is less than 0.05, et cetera, et cetera, et cetera on that one. All right. Does that help? Because once you sort of get the approach on these, they're all cookie cutter at that point. They all become the same thing, other than the equals, non-equals. Yes.
I had used a different script, and that might be where my confusion lay, because I was getting a p-value of like 0.99796.
Okay. Inside the R script, what it's going to do, what you have to do to that is you have to subtract that p-value from 1.
Aha.
And that would, so what that does is that gives you the probability under the curve. And what you want to do is you want the other probability of it being outside the curve.
Outside of it. Okay.
Subtract 1 from it, because essentially what you're doing is you're saying you've calculated this part right here, subtract 1 from the entire data set. You want that part right there.
Gotcha. Okay.
So And that is literally the approach for these. And these are fairly straightforward in terms of the hypothesis test, because the idea is you got to understand them and get them in terms of getting the approach down. Because once you get the approach down, it's gather data, pick the script, run it, and get some get some answers pretty quickly. And that's really what we want to do in analytics. Is we want, the key thing is, and you've probably, if you've been on these calls before or listened to the recording, is figure out what the problem is asking you first, and then how you're going to approach it. What model are you going to use to try and solve the problem? Don't even look at the data yet. Figure out from a big picture perspective, what am I being asked to do? And in the case of these hypothesis tests, is it an equals, not equals? Is it a greater than? Is it a less than? Well, take the more stringent approach to trying to disprove, or take the negative of what you're being asked for and say, you need to prove to me otherwise. Otherwise, I'm not going to believe what I'm being asked for. So Hugger Polls contends that an agent conducts a mean of 53 in-depth home surveys each week. A streamlined survey form has been introduced, and Hugger wants to evaluate its effectiveness. The number of in-depth surveys conducted during the week by a random sample of 15 agents is this data. At a 0.05 level of significance, can we conclude that the mean number of interviews conducted by the agent is more than 53 per week? Well, what you're doing is you have introduced a new streamlined survey, and you're saying that, well, I'm not going to make any changes to my process unless, or I'm not going to adopt this streamlined survey form unless it can be proved that it's actually doing something. So in other words, I want it to be greater than 53, but I'm not going to just take it for granted that it is. It has to be proven to me at a 95% confidence level that it actually is allowing or giving my agents the ability, given their time, to do 53, at least 53, or actually more than 53, not at least 53, because we're including the equals here. So it's got to be more than 53. So, and that's what it was being asked for, more than 53 per week. So you take the negative, no, this thing is not, prove to me otherwise, at a 95% confidence level that it is. Same thing, we're using a 0.05 significance level. So we look up on our t-table, given how many, 15, so degrees of freedom would be 14. We look this up in the table, we're going to get a critical value of 1.76, which is fine. If we use the t-test function, we don't even need to worry about it. It'll do it for us. We construct our hypothesis, prove to me otherwise. So no, this survey is not having any effect on my agents. It's not going to help me. So again, something like this, you aren't going to adopt or make a change to your process unless you can prove that the change to your process actually does work. And this is how you get confident and making business changes. And this is the reason why the analytics folks are so relied upon, because if you do these things in such a way where you're confident in the end that we saw some value in doing it, companies may spend millions of dollars investing in something based on this analysis, or they may decide to do something or not do something based on the analysis. So this is where the power of these kinds of things comes into play. They could have big effects on how organizations work. And, it could be a huge manufacturing company, it could be a small business where you decide to either buy something or not buy something, or adopt this new process or not, based on, maybe a trial period. Maybe you're going to try out a new piece of software, a new machine, or you're a lawnmower company, and you're going to try this new machine that'll do lawns 20 minutes faster, which can then allow you to do more lawns per week. And we're going to test it out. We're going to gather some times, and, all lawn sizes being equal, we're going to see if it makes any difference for us. And we're going to test it. 25 samples ought to be good enough. We're going to make a decision to buy it or not buy it based on that. So stuff's, real practical, and this is where we really get This is where the analytics folks, and again, informatics folks sort of had the bent towards healthcare, but this is where you have your big impact on the organization. So does that help? Good.
Yes.
Okay, good. Excellent. So yeah, I mean, if you haven't done week 9 assignment yet, you have questions 8 and 9 essentially done for you. Then they're right, and you can do them, and get comfortable with them, and they become essentially cookie cutter after a while. They become the same things, and just the approach that, again, it's think about what you're being asked to do, identify which model will solve that problem, and then go back, and then you can mechanically do it later on with the data. Don't try to jump right into the solution until you understand how to approach it. So, and that goes with all analytics problems, whether it's this class or some other class where you're going to do some analytics, or a job you leave. It's don't jump in and try to solve the problem until you understand it and you've got a good model that you're sure works for it. And then once you do that, gathering the data and then running the models is the easy part, and you can run it over and over and over again and see if it makes sense, because now you don't have to do this stuff by hand. So any other questions on hypothesis testing?
Yeah, I had one.
Yeah.
Yeah. When it's a right and when it's a left tail test, I had trouble in the R formulas figuring out how to modify those formulas to make sure I was getting the right or the left. Same
Okay.
with p-norm.
Yeah. So which script were you using? Because so some of those scripts actually do a lot of the calculations, and they give you a value, and then they calculate the critical value, and then they calculate the statistic for you. It's up to you to know. So in some of those scripts, it's up to you. If you use the t.test function like I just showed a second ago, it's going to tell you whether it's rejected or accepted, right?
Yeah, that one was easy because it has the alternate, and you tell it left or right.
Exactly.
But like the QT test, the QT formula,
right,
where it's 1 minus, and I
Yep.
wasn't sure which one to use.
So that's the time, and those scripts were done that way to make you think about what test you need, what region are you testing. So are you looking for so you have to find a critical value. Are you looking for a critical value? Are you trying to prove a critical value up here? Or are you trying to disprove a critical value here? Or are you trying to look for critical values here? So it made you determine how to use that, because the onus was on you, and it was done that way on purpose, because you had to know, now that I get a critical value, what am I looking for? What is my hypothesis looking for? It's looking for, now, and I'll just take this example right here. So we do the calculation, we get the critical value, and in this case, my data is going to give me the t statistic. It's up to me to know if that t statistic, depending on if it's greater than or less than or equal to the critical value, which region to be in. So it just gave you a piece of data and said, okay, this number compares to this number, how? Well, the t statistic number is greater than my critical value number. Oh, that must be rejection region. Why? Because my null hypothesis is less than or equal to, so it's this way.
Yeah, I was okay with deciding whether the test should be left or right. I wasn't sure how to manipulate the R formulas to give me left or right.
Okay. Okay. Do you have an example? In a case like that is a very specific, good question. That's when you want to reach out to me or the TAs, because once you get that guidance and understand how to use it, then it becomes very simple. So yeah, you definitely want to reach out to us when you have a question that specific, because you're pretty much on the goal line in terms of, you're like on first and goal on the 5-yard line. You're close. So all you need is that a little additional guidance on that script, and then you probably would have had no problem going forward with them. So yeah. Now again, I gave everybody 2 submissions on, what was it, week 8 or week 9, I forget now. One of those weeks from there forward. So if you find that, hey, I got a better way to do these things and you want to resubmit, go ahead and do that, because once you get that additional piece of understanding and it becomes very easy for you to do the analysis, then yeah, these problems become pretty easy, because they're not meant to be super hard. They're meant to be enough for you to have to think about how to construct these tests in such a way that you get them, and then you can construct them very easy going forward, and then you just plug numbers in. So does that help? Who was that? Was that Andrew?
That was John.
Oh, John. Okay.
It does help, and I kind of figured it out.
Good.
I did a lot of it in Excel at the same time, and I just played with R until it gave me the same results as Excel did.
Okay. All right. That's a decent approach. You learned a lot that way. Those two tools go hand in hand sometimes. I wanted you to kind of go out of your comfort zone, obviously, and do some as much as you could in R, but the last couple, 2-3 weeks, we'll use both. And you literally, especially in the analysis of variance and the regression, you can easily use Excel for those. R does a great job on those, and the scripts really crank through them, but you can use R or Excel as well, because they have built-in regression functions in there. So in correlation, Pearson correlation too. Very important, those Pearson correlations. And regressions are super important too, because if you, hopefully you're starting to get into that stuff now. In regression, you're looking for an explanation. So you're looking to try to explain what predicts something. So we had the example of let's see, predicting. I think the Apple would. We did some prediction on profits based on age as a predictor. That was the single variable hypothesis test. And I think we added some additional variables to see if we could increase the R squared, which is the predictive power of that regression function. Once you get R squares, above 80, you start to now really begin to get power in terms of understanding what makes up. So what factors drive the thing that I'm trying to measure. Regression is a very, very powerful feature capability, because it can help you when you have a huge data set. It can help you understand a dependent variable, how it acts, what levers and dials when they're changed have an effect on it. There's also a real estate one, I think, too. We got coming up in a heating cost example, if you haven't seen that one yet already, where there's a bunch of factors that drive heating costs based on attributes of a home, the size of a home, the furnace age, a bunch of other things. And once you get the hang of how to approach those things too, it's, there's lots of data, lots of problems you can solve, a lot of things you can begin predicting based on the data. Now I'm hoping we're getting very close to the end, just because the university just kind of shrunk the semester just a little bit. Stepwise regression is one of those that I was hoping that we're going to really spend some time on. I think we're going to get sort of shorten that discussion up. Stepwise regression is a very interesting thing. R does a great job at that. Excel, not so much. But in stepwise regression, you assume nothing and you begin adding variables in based on a data set. So let's say we're trying to predict the home heating cost again, let's say, for instance. And we're going to start off with maybe one variable, and then we're going to add another, and then we're going to add another, and then we're going to swap them out. So stepwise regression basically goes through, and that's why R is so powerful. It does it pretty quickly. It goes through all of the combinations of variables, independent variables, that make up the best predictor, and it ends up settling on the one with the highest R squared value. So you may, and stepwise is really great because you may have a huge data set and have no idea what really the predictors are. Well, you let stepwise regression figure it out for you, and it'll go through all the combinations of those independent variables and choose the best predictive model based on all these different values, all these different independent variables, and then it'll give you the confidence in the R squared correlation value. So that's kind of where we're headed. So this was sort of the kind of the introduction into that kind of thinking that you're going to see over the next couple of weeks. And literally it's like a couple of weeks, two less than 3 weeks. So John, does that help?
Yeah.
Okay, good. All right,
Uh,
good. Any other questions on this stuff? And again, reach out to the TAs and let me know if the TAs are not getting back to you. I know they're busy as well. They got schoolwork. Reach out to me. I'll help you out with this stuff. I think it gets a little easier. Hypothesis testing is one of those confusing ones, and you can sort of wrap yourself up and turn yourself around and end up not not having it be straight in your mind. But once you take that approach, the philosophical approach to how I'm going to do this, then it becomes a lot easier. And then I think correlation and regression are very simple, not simple, but there's a very methodical way going about doing those. And again, very powerful. So.
Can I ask another question?
Yeah, sure.
In week 10, the Gibbs baby food example,
Yes.
I think I'm having a little bit of trouble with the whole p-value
Okay.
thing on that one, because it's very high. It is what I'm coming up with for the question. The p-value is quite high.
Okay.
So I'm not entirely certain my analysis on that,
All right, let's take a look at.
or if I did it wrong.
All right, so is it one of the assignment questions or is it part of the lecture?
Yeah, it's one of the assignment questions.
Right,
It's
pull that up. Close, don't save, open.
yeah, it's one of the 2 sample ones.
Okay, so let's take a look. Let me pull that one up. Week 10.
Professor, I want to say thank you, but something's come up, so I have to go.
Oh yeah, sure, no problem. Good. I'm glad it helped. All right.
Yes, it has. Thank you.
Okay.
And this is recording, so I can see it again later with the stuff I'm missing.
Yeah, exactly. Yep.
Okay.
I'm recording it now, and I'll have it posted tonight.
Okay. Thank you very much.
All right. Welcome. All right. So let's go over to week 10. Take a look at week 10. Okay. Question. Any particular question?
I was looking at the first one, the Gibbs baby food. 65 observations. I don't know. Yeah,
okay.
yeah, the 65 observations with a standard deviation of 0.75.
Yep. Okay. So this is comparing two population this is comparing two population means. So the question is, conduct the following hypothesis test using a 0.08. So 65 observations selected from one population with a population standard deviation of 0.75. The sample mean is 2.67. A sample of 50 observations is selected from a second population with a 0.66. The mean is 0.259. Now, conduct the following test of hypothesis using a 0.08 significance. It's a one-tail or a two-tail. Let's see. They want to know. So is this the answer, not the question? So I don't even have the question. Let me pull the question up real quick, because in order to make that equal, not equal decision. Oh, okay. Yeah. So, all right. So that is the question. So the question here is, we've got two different samples coming from two different populations. Now we're trying to see, the question isn't clear as to which one is greater than. All right, so in a case like this, since we're not being asked to see if these two are equal, we have to assume one is different than the other. So the easiest or the simplest way and the most standard way going about it is one sample mean, and we're trying to Yeah, we're trying to compare one sample mean to another sample mean. Now, the best way to do it is always to take the less than equal as your null in a case like this, and then reject. So now we're working with a rejection region in the right tail. All right, so we're trying to compare two separate means. Now, we're given the population standard deviation. So when we're given the population standard deviation, we can use a z-test for that. When we're not given a population standard deviation, we have to use a t-test for that. That's kind of well, that is the statistical rule. So we're going to look for so if we look in the z table, we can either calculate it in the R script, or we can look in the z table for a value of 1.405. All right, so that's literally coming right out of the z table. Now, reject H0 if the rejection region is greater than 1.405. That is, shoot, that I don't have that up there, but this is that same one-tailed test that we were talking about in the previous example. So this is just mu1 minus mu2 divided by the standard by the square root of the standard deviations divided by n. So this is literally right out of the formula in the lecture. So this would be a two population hypothesis test when the population standard deviation is known. Does that make sense? That should have come right out of the PowerPoint deck.
Yep.
And then the z calculation is 0.06 or 0.607. So it is going to be less than the critical value. So we are going to go with this, and we're going to fail to reject, accepting the null and failing to reject it. All right. The p-value here is 0.2709, and again, we're talking about half of the curve, because we're talking about a z value now. We're not talking about the entire population. If we were doing a t-test, we didn't know the populations, because I think there's an example in here having you do a t-test with a pooled variance. If we're going to use the z calculation for this, we're only talking, the z only gives us half of the distribution. So we got to subtract our p-value from 0.0 or 0.50, or half of the curve. That's the difference between doing a t-test and a z calculation, because the z will give us half of the distribution. So the p-value is 0.207 or 0.2709, which is a pretty high p-value, so you really can't reject.
Okay, so with the script that we were that was suggested, the two sample hypothesis test lower tail Gibbs baby food example.
Okay.
My p-value calculation, I'm guessing is it just twice the value, because it came out, it calculated out as 0.5438015.
Okay. 0.54.
Yeah.
Same result.
Okay. Let me go back to that script. So is that the week 10 script as well?
Yes.
Let me go into that. And you used
It was two sample hypothesis test lower tail Gibbs.
lower tail Gibbs. All right, let me pull that one up. Baby food, comparing the weight. Oh, okay. Yeah, those were swapped. So the hypothesis was swapped on that, because this one was them being, so I have in that example, I've got the Gibbs being greater than.
Yeah, I had swapped it. All of my numbers line up with yours, with the exception of the p-value.
Okay, let me run this real quick here.
We're still seeing your Word document too. I don't know
Okay.
if...
All right. Yeah, let me run this real quick. 0.1. All right, let me switch over. Stop. I'd have to go back to the lecture too to see if these numbers align properly. All right, so we've got an X bar of 7.6. So population 1 of 7.6, population 2 of 8.1, sigmas of each 40. And okay, so just changing these numbers for the assignments basically. There's our Z statistic. Alpha is 0.05 in both of these. Is alpha 0.05 in this one too? It's
I
0.08.
think it's 0.08.
Okay, so I need to change that. Actually, I would need to change all these values anyway. Okay, so we're going to do the normal, okay, doing the normal distribution to calculate the Z value. All right, so that gives us the p-value of 0.150. So let me go key these numbers in because it's going to be hard to make apples and apples here. So population standard deviation of mean is 2.67. So X bar, can you still see my screen? 2.67?
Yep.
All right, X bar 2 is 2.59. 2.59. Sigma of 1 is 0.75. 0.75. And the sigma of 2 is second population 0.66. 0.66. We've got a 65N on population 1. And we've got a 50N on population 2. Okay, so let's see what we get for that. So I'm going to Control L and clear that. And run that. So we get a test statistic of minus 1.64485. Minus 1 point. That's even less than. So we're definitely not.
I think your alpha is at 0.05. That might have something to do with it. And I think
yes.
we're negating it because it was
the other
lower
way.
tail test.
Exactly right. Okay, so there's my critical value. All right, let's try that. And run that. P-value is 0.54380. Okay, minus gives me a probability of minus 0.043. Critical value is 1.405. Okay, 1.405, the critical value, that's correct. So that's correct. Now, Z value is 0.543. So 0.543 minus 2. P-value is point. So that says a minus 0.4. I should reject H0, so that's not correct. 2 times the normal. Did I need to do this? Yeah, so I needed to take out, because it's unfortunately that shouldn't have been double, so 0.27190. Yeah, I probably should have put that script out there because this p-value here was unfortunately, so that 2 times the p-value, that was actually used in a script, and that example is probably not even right either because this isn't an equal not equal. That would have been the proper p-value for an equal not equal. This isn't a p. So in other words, we want we want the rejection region and the entire curve down to the right in infinity, essentially. Here, what we're doing is we're calculating the p-value for an equal not equal, so we're using 2 rejection regions on this. So actually that shouldn't be that. That is what this thing should be. It shouldn't be. So that is actually left over from a 2-tailed test, and it shouldn't have been. Oh boy. All right, I'm going to go repost that script because that gives us a p-value of 0.2719, which is really what that p-value should be. All right. Yeah, let me repost that script because that 2 times, that was for a 2-tailed test, and it really should have come out of there because we just need the normal distribution for a 1-tailed test. So this is the proper way to do it. So that would have given us the other answer, which really didn't need that. That's this number right here. So all right, let me post that out there. I'm sorry about that. That should have come out. It's too hard for you to kind of know how to do that. So I'll repost that script out there. Does that make sense?
Yeah, that definitely makes sense.
Yeah. So if you take out the 2 times the normal distribution and just include the normal distribution of a z-value, it'll calculate the proper p-value based on this z that we calculated right there. Because it's taking essentially your test statistic and comparing your test statistic against the critical value. That's essentially what it's doing right there. Okay. Well, that makes sense. That makes me feel better. I'm thinking, I know that script worked. Okay. So you could also, well, for that one, we wouldn't use the t-test because the population standard deviations are known. So we wouldn't use the t-test on that one. The z is a better choice for that. And literally, quite literally, you could have done that part of it in Excel as well, and it would have been fine because I don't think I'm asking you to paste your code anymore, right? Don't think I'm asking you to do that anymore. Quite honestly, from the rest of these, the direction of the test will be different. I did say that in the document. I should have just taken out the 2 times in there. Okay. I'll repost that script. And that may help with the others as well. So does that help at all, Casey?
Yes, I think that I had been able to change the values to make it a 1-sided test instead of a 2-tailed test.
Right,
I think I just missed that 2 times.
All right.
Thank
Awesome.
you.
You're welcome. Any other questions? I'll repost the script out there for you. It'll be as soon as we're done here. Any other questions on this? This is probably week 10. Week 9 and week 10 are probably the harder, in my opinion, of the weeks. Although week 3 was challenging in getting the frequency distributions in the intervals set properly. Those are challenging, but they're good. You're always going to be called upon, if you're in this field, you're always going to be called upon to do stuff like that. So, all right. Any other questions? I'm going to post, I think, within the next week, a sample exam that you can take on Blackboard. It's not graded, but you can take the exam and you'll have all the answers to it as well. It'll help you in preparing for the final. So. All right. Any other questions from anybody?
And talk to you about the email contact that we've had and
yes,
response.
I answered that. Did you see that answer?
Yeah, I did have a couple more questions.
Based on that? Okay. All right, sure. All right, go ahead.
So the script that you sent me, it's for a single t-test.
Yep.
So because questions 3 and 4, those are paired t-tests. So like would I add in the like how would I
Yes, let's see here.
program to
Off
do
the
that?
top of my head. Can you still see my Word document?
Yeah.
Okay, good.
Wait, actually, no, I can't.
You can't see the Word doc? All right.
Professor, I'm just want to say thank you again. I have to
Okay.
run after a toddler.
All right,
Thank
yeah, no
you.
problem. You're welcome. All right, good. All right, let's see. Real quick here. I'm going to give you a link. T-test parameters. Let's see here. Okay, so here is a good, I'm going to pull up my screen here. Here is a really good ourdocumentation.org, a real good explanation on the different kinds of parameters that you can have in the t-test. So one of them, if you needed a two-sided test, you could put the two-sided example or the two-sided parameter inside of your t-test. Now you don't need all of these parameters, but you can use the t-test in R for all of the situations that you need to do t-tests on. So it could be a left tail, right tail, two-sided tail, a paired t-test, looking at pairs, two pairs of data sets and comparing two pairs again together. Here is a really good example of how to do that right there. So in this case, we've got, they actually put all of the different parameters in there. So if you're doing a paired t-test, you would say paired equals true, otherwise it's paired equals false, or just don't include it because the false is the default. And literally you don't need all of these things in there. You saw in my t-test example, I had an alternative equals greater than. So I had that option in there. This option gives you the alternative less than. So this gives you the lower tail. So this would be the lower tail rejection region. And this gives you a two-sided. So you only use one of these at a time when you're doing your t-test. Now they're showing them all here just so you can see all the different options on it. But this is a real good website for that kind of thing. So two-dot-sided, alternative equals two-dot-sided in double quotes for two-sided test. Alternative equals less in double quotes for the lower tail rejection region. Alternative equals greater for the upper tail rejection region. If you're doing a paired t-test, you set paired equals to true. Variance is equal would be depending on the problem you're given. If you're given a problem where the population variances are equal, then you would say true to that. More likely than not, it would be false. So you just wouldn't include that parameter. But if you were given a problem where the variances of the populations were exactly the same, then you would say var.equal equals true. And then it's assumed 95% confidence level is assumed. So if you have a confidence level that you want other than 95, you'll just change the conf dot level equal to 99, let's say, for instance, or 90. But for the most part, those the T example should be able to help you. So that's a good question though, because I don't think I have an example out there on a two-sided t-test. Does that help?
Yeah. So so the default version of the script it says so it has table data to represent the one set of data. So
Yep.
what I can do is like just hit enter and on the next line write like table data 2 and do the same stuff and
exactly.
then put that in the result.
Yeah, let me go pull this up real quick. There's the t-test function right there. So yeah, so you can either put your data in here using this C function, which is concatenate function, Or you can do, just like we've been doing, is read a CSV file, and then you change your value here, greater or less than. So less than would be the lower tail. Change that alternative to less than and be the lower tail. Or change that, actually you don't even need to say less than, you just say less. And if it was and you notice here how I have the conf level being 97.5, because I need to override the default of 0.95. And if it was two-sided, you would say, so if it was a two-tailed test, you would say alternative equals 2-tailed in there. So, or 2-sided in there. And then you can make that t-test be a two-sided t-test. And then it's, pretty easy. There's your table data. You can do table data here, or you could do table data $ shelf life, which kind of has been the progression that we've been doing. The only reason why you don't have to do that here is because shelf life, LIFE, and the reason you don't need to do that here is because that's the only column in the data set.
Yep.
That had it been, another, had it been multiple data sets, then you would need to tell R which of the values you wanted. So I only have one here. Let's see if my data set's still there.
Or
Yeah.
could I create another variable like line below table data, like write table data 2 and then list the data set for it afterwards, and then I could put a comma after table data on the t-test line?
Well, for like two data sets, you mean for a two-sided?
Yes.
Yeah.
Well, on a paired test, like
a paired t-test. Yeah. So a paired t-test, what you would best thing to do for a paired t-test would be to put both columns of data inside the same Excel and just say shelf life and then table data dollar, whatever your other column is. Let's call it column 2. And then alternative, so it would be alternative 2-sided. And that would give me a, now in a case like that, I have to have more than one, I need a comma in here. I'm gonna need, actually, in a case like a two-sided t-test, you're going to need 2 population standard deviations, or I mean 2 population means, or you don't specify the population mean at all in here, and you let it calculate it for you. All right. So if you wanted to, see if we can find an example here. That's a 2. Yeah, this example. Okay, here. Yeah, let me just jump over to this R real quick and show you what a 2-paired would be, or a 2-sided would be, or a paired. Here it is, paired. So here's a paired R script example. You don't need to then specify the population means for those. R will calculate it for you. So I don't know, let's see, the data set and the sleep data set actually has pairs of measurements. The same people were tested with each drug. This means that you should really use a paired t-test. So there's a paired t-test in the 2 columns in here are extra and group, and the data is the sleep data set. So we could, and then let's run that real quick. And here's an example. Here's a t calculation there with a decent p-value. And again, since it's a paired t-test, it's going to be testing that the means are equal or not equal. So a paired t-test is always about an equal, not what's greater than or equal to. So basically what you're trying to do is you're trying to compare two population means together with a paired t-test. So lots of really good examples of using the t-dot test in this R documentation. And there's tons of R documentation as well. If you Google t-test, paired t-test example using R or something like that, you know, you'll easily come up against it. So that's a pretty good example right there. Does that help?
Yeah,
Okay,
thanks.
good. Excellent. Yeah, very powerful. You know, I wanted early on you to kind of do some of the mechanics around it. Once you get the mechanics down and you understand the mechanics, like the t-test that we did a lot of work in there. We did a lot of calculations in there, but R makes them pretty easy. All of these big tests that you can do basically have a one-line function, and you just pass the parameters to it. It does it very quickly and easily. So that's why I introduced this one here. And the correlation and regression are similar. They're simple one-line function calls. So, all right, good. Any other questions?
Yeah, I have one more about question 5, which it seems like it's pretty similar to question 1, except I need to find the critical value.
Okay, so question 5 in which week?
Week 10.
10, question 5, 4, 5. Okay. So public and private adoption agencies. All right. So a recent survey compared the cost of adopting through public and private, simple or a sample of 16 adoptions through a public. Mean cost was that. Standard deviation of that. For a sample of 18 adoptions through a private, so we've got an n equals 16 and an n equals 18. Mean cost was that with a standard deviation of that. Can we conclude the mean cost is larger for adopting children through a private agency? Again, prove to me otherwise that it costs more to adopt children through a private agency. So prove to me otherwise that it costs more. So that means we're going to assume that it doesn't. And there's your hypothesis test, that the private is less than or equal to the public. And our alternative is the private is greater than. So in other words, prove to me otherwise based on my data and based on, the key here is that's going to be driven pretty heavily by this, which is 16 sample and an 18 sample. Your degrees of freedom is found by this formula right here, which is right out of the lectures. All right, but you could actually do that same t-test. So you could literally key these values in using the t-test, but you know, using the formula is pretty easy as well. So as soon as you set your hypothesis test up properly, using so this is a comparing of two populations. All right. And it's based on the week 10 lecture. Here's the formula for calculating degrees of freedom, because we're going to use the degrees. We have to essentially mesh or normalize the fact that we've got two different size populations. We're trying to make a decision on these. So we've got to normalize the degrees of freedom by using both degrees of freedom and the variances, or the standard deviation. So the standard deviation squared divided by n, standard deviation squared divided by n, all of that is squared. So what we're trying to really do here with these two populations is we're trying to smooth out the differences in, because these two populations have different variation or different standard deviations, and they have different sample sizes. So this formula smooths all of that out to try to get a single number. We use that degrees of freedom number to get a t-value. So we literally will use 27 as the t-value. We want a 0.05 significance. Look that up, or we could calculate it. I don't know if I have an R script. Did I tell you which R script to use for this one? I don't think so.
Well, I've been switching back and forth a little bit between R and my Word document, and it looks like the Gibbs baby food can be used for question 5.
Okay. Yep. All right. So if you can use it, I don't know if I told you one, but literally you could use that script by keying the numbers in, or you could go into the formulas in the lecture material, key these values in. Actually, that degrees of freedom calculation would be easier if you did it in our script. Then you need to calculate a critical value. Did you get a 1.706 from the script for your t-value? That's actually the Gibbs baby food is a Z. Okay, because we know the population standard deviation, so we can use that Z calculation. Why did I use a T here? So for sample cost standard deviation was that. Because we've got 2 populations. All right. Why did I use that versus a Z? I'll have to think about that one. Population standard deviation and the mean is that. Population standard deviation and the mean is that. What makes that different than this one? Why did I choose that? Because we don't have, so these are samples. All right, so these are samples and not the populations. That's the difference. Let's go back up here. Yeah, that's the difference. The subtle difference between this problem, so notice we have the populations, and that's part of the reason why that this homework is the way it is because the word population here, since you know the population, you can use a Z value. Here, we don't know the population. All we know is the sample. We can't use a Z value. We have to use a T value at that point. So what you're going to do is bounce this problem off of the methodology or the model in lecture that said we want to compare 2 populations with unknown population standard deviations. That's essentially what this is. That's why it's a T test and not a Z test. Does that make sense?
Yeah.
That's literally the difference right there. I mean, it's all about knowing your population. And if you don't know your population, which can kind of guess in some data set as big as this, we wouldn't. All we would know is samples. We have to use a t-test at that point. Okay.
All right.
Good.
Thanks.
Yeah, good. No, that's good. These are good questions. I mean, this is the kind of stuff that helps you dig in and really become number savvy, you know, and really get good with your analytics. So it's just one step in your journey. All right, good. Any other questions?
None for me.
All right, good. John, Andrew?
Good now.
No, this was very helpful. Thank you.
Okay. All right, guys. Good luck with all that. And, you know, if we need to have another Zoom before the end, we can do that. I have one script change I got to get out